All right, today we're diving into a really fascinating paper from Meta AI. It tackles one of the biggest, most persistent headaches with large language models, factual hallucination. We're going to be unpacking their proposed solution, a methodology they call chain of verification, or CoVe for short.
So, here's our game plan. First, we'll quickly set the stage with the hallucination problem itself. Then, we'll introduce the chain of verification method. After that, we'll get into a crucial detail, the difference between factored and joint verification. Then comes the fun part, the results, before we wrap up with the key takeaways.
Okay, first up, let's talk about the core challenge. As we all know, even as these models get bigger and more powerful, they still have this nagging issue of, well, just making stuff up. This problem, hallucination, is a fundamental barrier to their reliability.
So what do we mean by hallucination? It's when a model generates a response that looks and sounds totally correct. The grammar is perfect, it fits the context, but the facts are just plain wrong. And you see this happen all the time with more obscure, long-tail information that wasn't very common in the training data.
Now, this is where it gets really interesting. Check this out. On the left, the model is generating a list and confidently claims Hillary Clinton was born in New York. Totally wrong. But then on the right, you ask it a direct, simple question. Where was Hillary Clinton born? And it nails it. Chicago. This is a huge clue, right? It suggests the correct information is in there somewhere, but the model struggles to access it reliably during more complex tasks. And this observation leads to the central question of the whole paper. If the model kind of knows the right answer deep down, can we prompt it to deliberate on its own output? Can we get it to check its work and correct its own mistakes without having to use any external tools?
And that is precisely what the authors set out to do. Let's get into their proposed solution, the chain of verification method, which is all about prompting the model to perform a systematic self-check.
The entire CoVe framework really hinges on this one core assumption, that a capable LLM can be prompted to not only generate a response, but also to devise and then execute a plan to fact-check that very same response. It's a really elegant four-step loop, all performed by the same language model. First, it generates a baseline response, warts and all. Second, it looks at its own response and plans a series of verification questions to check the facts. Third, it executes that plan by answering each of those questions. And finally, it takes those answers and revises its initial response to produce a final, verified output. And this diagram from the paper lays it all out perfectly. You see the initial query, which leads to a flawed baseline response. Then the model plans its checks, asking questions like, where was Hillary Clinton born? It executes those checks, gets the correct answers, and then uses that information to generate a final, corrected list, completely removing the hallucinated items. Now there's a critical detail buried in step 3, executing the verifications. The paper makes a really important distinction between two ways of doing this, what they call joint verification and factored verification. So in the joint method, the model answers its own fact-checking questions while it can still see the original, possibly wrong answer in its context. With the factored method, however, each verification question is answered in a completely separate, isolated prompt. The model has no context of its initial baseline response.
The insight here is pretty brilliant. The factored approach is all about mitigating a kind of self-confirmation bias. By removing the initial response from the context, you prevent the model from being primed by its own mistake. You force it to recall the fact independently, from scratch. And as it turns out, this methodological nuance makes a huge difference. So, let's get to the good stuff, the numbers. Let's see how CoVe actually stacks up on a few tough benchmarks.
Okay, for list generation tasks, the results are pretty striking. On Wikidata, CoVe more than doubles the precision of the Llama 65B baseline. And look at how it does that. It absolutely crushes the number of hallucinations, dropping the average number of wrong items from nearly 3 per response down to just 0.68. It's a massive reduction in errors. We see a very similar story on the MultiSpanQA benchmark. The factored CoVe method boosts the F1 score by a relative 23% over a strong few-shot baseline, jumping from 0.39 up to 0.48. And that's a healthy gain across the board, improving both precision and recall.
This chart really puts that jump into perspective. It's a significant leap in performance. And just to hammer this point home, this gain comes purely from prompting the model to deliberate on its own answer. No fine-tuning, no external tools.
But honestly, the results for long-form generation are maybe the most impressive of all. Using the FactScore metric,
The baseline Llama 65B model scores a 55.9. With CoVe, that score skyrockets to 71.4. Not only does that blow past the baseline, it also outperforms both ChatGPT and even the retrieval-augmented Perplexity AI.
I mean, a 28% relative increase in factual precision for long-form text is just a massive gain. And it's so critical to remember this is all happening at inference time through structured deliberation alone. No changes to the model's weights, no access to a search engine.
And this graph shows us something really nuanced about where CoVe excels. It breaks down performance by how rare a fact is. And sure, for the super obscure, long-tail facts, a retrieval system still has an edge. But for the more common and medium-frequency facts, the head and torso of the knowledge distribution, CoVe's deliberation process actually outperforms retrieval.
So let's bring it all home. What are the big takeaways from all this? Well, the paper offers some really clear, actionable insights for anyone trying to build more reliable reasoning processes into these models.
So a few key conclusions. That factored verification approach is consistently better. Letting the LLM generate its own questions works better than hard-coded rules. Open-ended questions are better than yes-no. And it validates that core idea we saw earlier. Models are just more accurate answering short-form questions than generating long-form text. And interestingly, they found that standard chain of thought prompting didn't really help on these specific factuality tasks.
Of course, it's vital to acknowledge the limitations here, as the authors do. CoVe is a powerful tool for mitigating hallucinations, and it reduces them substantially, but it's not a silver bullet. It doesn't eliminate them completely. The model is still ultimately bound by the knowledge stored in its parameters.
But really, what this research does is demonstrate the incredible potential of structured deliberation. It points toward a really exciting next frontier, where you can imagine combining these internal deliberation methods like CoVe with external tools like retrieval to create truly robust and verifiably grounded AI systems. And that, right there, is the goal we're all chasing.